Good. We get to pretend the last couple of minutes didn't happen. So do you have a leaving group? Yes. What is it?
Bromide.
Bromide's a leaving group. That bromide is on a tertiary carbon, right? The carbon the bromide's on has got 3 other alkyl groups on it. And that means you cannot do Sn2. So any substitution product is going to be the result of an Sn1 reaction. I said all that. I don't need to write it. Now, do you have a strong base? No, you do not. Water is not a strong base. Neither is ethanol. Those are the 2 sort of common liquids that we can latch onto, right? You guys have seen ethanol burn. If you drink straight ethanol, it burns on the way down, but it's burning not because it's a base, all right? Don't do this. Humans can tolerate like a shot of Everclear. Like, it's not good. Don't do that. I'm not saying don't drink. I'm saying don't drink a shot of Everclear. You can't tolerate like a shot of 1 molar sodium hydroxide. That would burn in a completely different way. All right? And there are lots of terrible stories. Like, you can read about this if you want. There are kids that get into Drano. Drano is basically really concentrated sodium hydroxide. Like, if you don't lock that up at home, you got kids, they can get into it and do a lot of damage. Okay, but water, ethanol, these are neutral, like there's pools of water laying all over the place. Nothing happens. Water is not a strong base. You have a good nucleophile. Like, all you got there is water, right? So if water is not a strong base, it's also not going to be a good nucleophile. Now, to complicate your life, there are molecules that are good nucleophiles without being strong bases. And we'll go through some of those next week. In this case, water is a weak base and a weak nucleophile. All right? Even if the bromide weren't on a tertiary carbon, without a good nucleophile or a strong base, the reaction is not going to be Sn2 or E2. Sn2 and E2 are driven by the base, or the nucleophile, right? Everything happens at once. The new bond forms, the old bonds break. That has to be driven by the reactivity of the base or nucleophile. Here, in Sn1 or E1, we're going to lose the leaving group. What's going to drive this reaction is loss of the leaving group. Okay, so you might have swapped in water for bromide and left OH2 on there. That is not the product. The product of this, the substitution product, sorry. This is aqueous. So this reaction is actually run in water. Water is the solvent. So this reaction is called the solvolysis. If you run a reaction where the solvent is also a reagent, those tend to be called solvolysis or solvo whatever the reaction is. So it's an Sn1 reaction, and I've eliminated the stereochemistry there. Right? So we start with whatever the optical activity. So 4 is out. It's going to be an R chiral center. The product is racemic, R plus S. And the reason for that is we go through this carbocation that's planar. Like, once the bromide leaves, that carbon is no longer chiral. It's flat, it's got a plane of symmetry through that plane. Nucleophile can come from either side. We get aqueous HBr, so the bromide's going to come off, water will attack, and then Br will take that proton. So let's look at that. I'm going to draw the mechanism for the Sn1 reaction first. So this is our slow step. This is our rate determining step. And you can see this chemically, right? We're breaking a covalent bond. Up until now, maybe this week, if I had drawn that molecule with the bromide on there, I did this all throughout, like, I probably drew molecules like that during the stereochemistry discussion. And never once did any of us say, oh, well, couldn't that bromide bond just break, right? That's a covalent bond. It seems strong. And it is. That's why this is the slow step. Sn1 and E1 are slower intrinsically than E2 and Sn2. So if you have a strong base or a good nucleophile, Sn2 and E2 are going to be faster. Let me put that in writing. Okay, so if Sn2 or E2 are possible, those reactions happen. So if you have a strong base or a good nucleophile, strong base will do E2, good nucleophile will do Sn2. If those reactions are possible, they happen. Sn1 and E1 are going to be slower than that. Yeah?
I'm just confused where you got the additional carbon.
Sorry?
There's like one more carbon on that chain.
Did I put an extra carbon in? Well, no, I think. I can't solve this. Maybe I did. Yeah. No, it's when they change positions like that. Yeah. So it's 5-methyl. Yeah. All right. It's okay. What's that? Are you okay?
I'm confused on how it rotated like that.
Yeah. So basically, carbon 5 here just planarizes.
Oh, okay.
Right. So this ethyl is swinging up here.
Okay.
Yeah. And you could draw it down. I could put the methyl up here and the ethyl down here. Again, the key is that it's planar. And yeah, looking at it is confusing. So numbering them is actually probably not a bad thing to do. I promise I take no offense at that. I promise I have drawn molecules with the wrong number of carbons in here. Right? It's unfair in the way life is unfair that I will probably take points from all of you at some point for doing that, and I'll do it in here and just laugh it off. All right, so I try not to make it a big deduction. It is an easy thing to do to put the wrong number of carbons as you draw molecules to transpose the number of carbons. Okay, so like I said, this bromide sitting by itself, if I made that bromide and it was optically pure, 100% EER, and I put it in a vial, put it in the freezer, like it will sit there. It will be fine. Okay, because what will happen if it's alone, the bromide comes off, and then nothing else is around, it just goes right back on. Now, over time, that bromide will actually racemize. Because that bromide could come off, and then everything swims around a little bit and it attaches on the other side. But if it's really cold, that's going to be slow. And like I said, when it comes off, like it's got to move. It's got to get to the other side. The most likely thing to happen is it just slams right back on from the side it came from. All right, so this is a stable molecule. You can isolate it, put it in a vial, probably ought to put it in the freezer, it'll be fine. But if there's something else around, okay, so water is the solvent here, so there's a lot of water. There's always more solvent than there is of the other stuff. And water is a stronger base than Br minus. Right? If I dissolve, if I have HBr and water, this goes to H3O plus and Br minus. All right, so the pKa of H3O plus is about 0, pKa of HBr is -7. So this reaction favors the right pretty severely. So we've got a whole bunch of a stronger base. So now once that bromide comes off, it's gone. Like once that thing comes off, now there's water in here, and for Sn1, the water is going to attack. Right? Water's got a lone pair of electrons there. It's got 2 lone pairs, but one of the lone pairs makes a bond to that positively charged carbon. Now, if I had asked you to draw this mechanism, you might have thought hydroxide should do this. OH minus, because you get an OH on the carbon, right? But there's nothing in there to make hydroxide. You don't have a base that can pull a proton off water to make hydroxide. Proton's not going to just pop off. So what happens is water attacks, and again, it can come from either side. that carbon is now racemic. It doesn't really matter how you draw it. You don't have to put wedges and dashes in. If you see a chiral atom drawn with no wedges and dashes, just 4 in the plane bonds, doesn't mean they're planar. It means the carbon's tetrahedral and racemic. All right, now, another molecule of water takes the proton. And this takes you up to the product. Now, all 3 of these reactions are reversible. Okay, the other thing, you could have used a bromide here if you'd wanted. I'm not going to get too worried about this at this point. If you use the bromide to take that proton, you get HBr. And that's kind of what I said the product was. You get HBr. HBr in water is going to exist as H3O plus and bromide, just like over here, right? The key point here is you don't remove a proton from the oxygen in water until it's positively charged. Okay, so you don't have a strong base. That's one of the first things you decided about this reaction is there's no strong base. That means you can't make strong. You can't just invent a strong base. If I just say H2O turns into OH minus, I've just created a strong base. So you have to wait, you have to wait until right here, now we've got the oxygen bonded to a carbon. This H is now way more acidic than water. Water's got a pK of 15.7. This is going to look like H3O plus, so the pK is going to be around 0, -1, something like that. Right. Now, once it's a super strong acid, now water can take that proton. Okay? That's Sn1. E1, the first step is the same. So let's see here. Sn1, Sn1. So your elimination product I'm going to draw, so the elimination product, you're always going to make, should put some alpha and beta here. So carbon 5 is the alpha carbon. So this molecule has 3 beta carbons. And you're always going to get a double bond between one of the beta carbons and the alpha carbon. So the carbon of the leaving group has to be involved in the double bond, and one of the carbons it starts out bonded to. And so we've got several possibilities here. So 4 carbons and then the double, 3 carbons. Right, so you've got, if we make the double bond between 4 and 5, we can have E and Z isomers. We could make the double bond between the methyl carbon and carbon 5. There's only one of those that you can get. And then we could make the double bond between 6 and 5. So 1, 2, 3. Right. So you can get a double bond between the methyl and C5. You can get E and Z between 6 and 5, and you can get E and Z between 4 and 5. That's a mess. What's the least stable alkene in that column? You can look at this board over here. Yeah.
Would it be the bottom?
It is the bottom one. The bottom one is di-substituted. There's only 2 groups on that alkene. It's the only di-substituted alkene. The other 4 are tri-substituted, and you've got E and Z, so that's 1. This one's going to be Z, that one's going to be E. all four of the tri-substituted alkenes have some steric instability. They're not going to be exactly the same stability, but they're going to be awful close. All right, let's go through, let's do the mechanism to get to one of these. So I'm going to do the one that the proton comes off of carbon 6. All right, so these cations are the same. And now water, instead of making a bond to the positively charged carbon, makes a bond to the H. The CH electrons then make a pi bond with that p orbital. And remember, right, in this hyperconjugation over here, in that carbocation, the beta hydrogens are, the electrons in that CH bond to the beta hydrogen are already interacting with the p orbital. So that proton is set up to be grabbed by a pretty weak base. And that instantly gets us really to either one of, that's the same mechanism to get to either one of these. So that, all five of those alkenes are produced by something like that. You've got a beta hydrogen that's already interacting with the vacant p orbital on the carbocation. A base comes in and grabs them. Similarly, and we'll talk about this maybe some next week, these are all reversible reactions. Right? We don't start off with anything super strong, and we end up generating a pretty strong acid. So this is going to generate H3O plus and bromide. Like, you're generating aqueous HBr, which is a strong acid. How's everybody doing? Yeah, good. Now that hand wave. 11 minutes. That'll do it. All right. So contrast Sn1 and E1 with E2 and Sn2. Sn2, the nucleophile drives the reaction. You get a concerted one-step substitution. You've got the stereochemical bit, right? The nucleophile has to come directly opposite the leaving group. So you invert the stereochemistry on the chiral atom. In the Sn1, we make a carbocation. You lose all trace of stereochemistry. So whether you start with an optically active bromide or a racemic bromide, doesn't matter. You're going to get a racemic product. And the reaction is driven by the leaving group leaving. Okay, so what this means for both E1 and Sn1 is the better the carbocation is, the faster Sn1 and E1 are. You have to be able to make a relatively stable carbocation, and then the faster that carbocation is, the faster these reactions go. So Sn2 does inversion, Sn1 gives racemization. In E2, remember, the base has to come and grab a hydrogen that is anti-coplanar to the leaving group. And that means E2 reactions tend to give fewer number of products. E1, any beta hydrogen is going to be interacting with that carbon center, is going to be quite acidic. And so you're going to get pretty much this, you're going to see pretty much equal amounts of these top four alkenes out of this reaction and a little bit of the bottom. So another thing here is E1 and Sn1 are a good bit less selective than E2 and Sn2. I haven't even touched on cation migrations, carbocation rearrangements, which we will next week. We've got a couple of things left to finish today. So Sn1 and E1, practically speaking, are much worse reactions to do in the lab. We tend to avoid making carbocations if we can, unless we need it to happen that way. So how would you tell? Like all I did here is I gave you a substrate and water. It's not much to go on. So if I'd given you this reaction, substrate, water, and asked you to predict the product, what would you answer? Like today, you probably would just skip it. Like, you know, if your worst night, hopefully this is not your worst nightmare, but if that classic student nightmare of, you know, waking up and forgetting you had an exam, and I don't know. And I hate to tell you this, you'll have this for the rest of your life, or at least I keep having them, right? Like this stress dream of, I forgot something important. In some region, we manifest it with school. Like school, at least in the United States, seems to do, I don't know about significant, but lasting, makes a lasting impression on you. Okay? So, exam 2 is today. I put it down in front of you. You come to this question. You probably leave it blank today. But what do you, take a stab. What do you think you should draw? Given what you've seen so far.
Well, we first have to identify the leaving group, I guess, and then, you know, water's going to be acting as a weak base. So, based on what we saw here, it seems that what you get is an OH attachment.
So, you're going to draw the substitution product. That's a fair bet. Like, honestly, and that would do it. Okay, so if this is all I give you, maybe it's not clear what I'm saying. If this is all I give you and I ask for a product, substitution product, if you draw the right Sn1 product, you'll get it right. Honestly, if you drew, certainly today, if you did this today, I'd be like, hallelujah. If you drew any one of these alkenes, that'd be fine. In reality, given no information, all these alkenes and the racemic alcohol are likely products. So if we do this reaction, if I take that optically active bromide that took me 6 months to make and purify the enantiomer, and I drop that into water for half an hour at room temperature, I will not have any of that bromide left, but I'll have all the other stuff. It'll be a mess. Okay? The last thing I wanted to leave you with, the piece of information that you really need here to figure out one or the other is the temperature.
You need to figure out if it's Sn or E.
Yeah. Is it Sn1? Is it substitution or elimination? And then I'm just going to tell you this. You can. Then I'll explain it. All right. Eliminations are favored over substitutions as the temperature goes up. So at higher temperature, elimination is favored. So what's a high temperature? Anyone? Well, I'm in water, so if I want the elimination product,
It would have to be below the boiling point.
well,
Because it won't work.
it would be at the boiling point, right?
Yeah.
If I want the elimination point, the easiest way to set the reaction set the temperature of a chemical reaction is to do what we call reflux. Have you guys refluxed in lab yet? Should talk to Dr. Keeney. Reflux is boiling. Reflux is a fancy way of saying boiling. You put a condenser on top of the flask, so your reaction flask where you put everything, put a condenser on top of it, and then heat the solvent to boiling. All right? At the boiling point of any solvent, the temperature stays steady. Of course, normally, if you do this at home, right? So we made pasta last night. In principle, if I start the pasta boiling and then I just leave, it's going to stay at 100 degrees. That's safe. I can walk away because that is going to stay at 100 degrees. So long as there is water there. As soon as the water all boils away, now the temperature is going to skyrocket. I'm going to burn my pasta. Eventually going to have a fire. I'm not going to have a house. But as long as there's water there, the temperature inside the pot is 100 degrees. So the condenser, in a reaction, we boil the water. Water evaporates, comes up, hits the condenser, condenses, falls back down. So you never lose water in the flask. So for this reaction, if I want this to be elimination, I boil the water. If I want it to be substitution, I do it as close to zero as I can. I do this in a flow chart. I cannot just tell you what a high temperature is and what a low temperature is, because that depends on the actual molecule reacting. There are molecules that to do substitution would need to be at like minus 100. Or that will do substitution at 150. So it depends on the molecule. In general, I sort of set 40 or 50. Right, we're at about 25 right now. If you're above about 50, I'm going to call that high temperature. Below, low temperature. And the last thing is, elimination's favored at higher temperature. Enthalpically, substitution makes sigma bonds, so the bonds are stronger. Elimination makes a pi bond. Right? A sigma bond stronger than a pi bond. But when you do elimination, you actually break this molecule up into two. So the disorder increases, entropy increases. Remember that equation, delta G equals delta H minus T delta S. You multiply the entropy by temperature. And so that the equilibrium actually changes with temperature. At higher temperatures, the entropically favored process is going to be more important. That's elimination in this case. A lot of stuff to look at. I know you got a lab spectroscopy work set to do. What I've been telling people is, if you got to go. What I've been telling people to do is focus on the lab spec right now. Once that's turned in, we'll come back and revisit it in here. So right now in here, be working on acid base and chapter 7. Have a good weekend, dude.
Thank you.
Look, you guys are on TV.